Hi everybody. In this video we're going to start talking about rigid bodies. That's chapter 11 in your textbook. So this set of lectures is going to go along with that. So in particular, what a rigid body is let's take a disk. If you have little parts of the disk, little pieces of mass, and you denote them a little bit, they have an orientation with respect to one another, and as that disk moves through space, the orientation of any two pieces of the disk remains constant. It doesn't change the orientation with respect to each other. And that's what makes a rigid body. Now before, when we looked at the kinetic energy of such a rigid body, we had 1/2 I, the moment of inertia about the center or about the axis of rotation, and omega squared. When we did the problems like this, so when we've done these problems in the past, we've always had the axes of rotation go up maybe through the center of the object. And if you remember, the moment of inertia can be found by, let's say, we have the density of the object and the volume. That's the mass. That's a little dm. So it's really this dm r squared. So r is the distance from the axis of rotation to each little piece of mass, and that's the mass r squared. So that's our moment of inertia. But we're going to see that we need a different moment of inertia to deal with rigid bodies in general. Specifically, let's say we have this disk that's rotating, but it's rotating about this axis. So then we're going to need a different type of moment of inertia. So what we're going to be talking about are tensors. You're probably familiar with tensors. You know that a scalar is a tensor to the 0th order. So it has one component. What we call a vector is a scalar to order 1, or a tensor to order 1. So it has 3 components, and this is called a vector. And a tensor to the 2nd order has 9 components, and this is what we're gonna call a tensor, but this is specifically what we're gonna have in this case. So tensor of instead of order, they usually call these rank 0, tensor rank 1, rank 2. So we're going to be looking at tensors of rank 2. So why do you need such a beast? Let's look here. So I'll note that what we're going to do today is a derivation of the tensor formula. So bear with me. So to start, let's say we have a mass and it revolves around some axis, omega. Now, let's say it's a circular orbit, radius of b. I guess for this example, let's just call it r, radius r. Okay, one of the things I want to remind you of that we talked about in the last chapter, if I take the time derivative of a vector as seen from the fixed frame. It's equal to the time derivative as seen from the rotating frame plus omega cross r. R locates the object from our origin. So in our rotating frame, in the frame of the mass, we'll write v rot is equal to let's say it thinks it's moving 0 velocity here, so we also have omega cross r. But now let's assume that the whole thing, the mass just moves off to the right too in translational motion. So let's say so even if we have more particles than this, the whole system is moving with big V. So we'd have to add that on. So that's some translational motion of everything, not just rotation. So our kinetic energy is going to be equal to 1/2 m velocity squared as seen from the rotational frame. So we're looking at the kinetic energy with respect to the rotational frame equals 1/2 m big V up at that first plus omega crossed r squared. So when I square that, I'm going to get this 1/2 m. I'll get a big V squared plus 2 big V dotted into omega cross r plus omega cross r squared. Just doing the FOIL method there. Okay, so now let's say that there are many particles, masses, and they always remain fixed relative to each other. So let's say we have the beginnings of a rigid body. So we got more than one mass, and they always somehow, maybe they're connected, but they stay at the same orientation with respect to each other, but we have n of them. Okay? So what happens to this kinetic energy? Well, there are they're all moving at the same translational velocity. And they're all rotating with the same omega. But they have different distances, and they're numbered, their masses are numbered differently. So let's write this as 1/2. We have n masses. Let's say this is alpha, m alpha, v squared, so that's the translational kinetic energy, plus 1/2, need to do the sum, alpha to n, m alpha, but I have a 2 here, so I cancel out the 1/2, so then I have plus 1/2 sum of all the alpha masses, omega cross r alpha squared. So that's what our kinetic energy now looks like. Now, remember, let me move this up a little. Our alpha locates each of the masses, so we can write that as instead of x, y, and z, I'm going to write x1, x2, x3. So x1 for this alpha in the x1 direction plus x2 alpha, x2 direction, plus x3 alpha in the x3 direction. Okay, and also omega can be written as omega 1 plus omega 2 plus omega 3. And again, I don't put an alpha here because all of them are moving with the same omega. Okay, so now I'm going to rewrite the kinetic energy. In terms of, I'm using x1, x2, or I'm going to use xi and xj. And for now, I'm going to forget the translational part. So this is the translational. And then this stuff must be the rotational. So let's look at the rotational. 1/2 sum. Oh, I guess I got to be a little careful. Notice this first term up here in the rotational part. The V and the omega don't depend on the indice alpha. So I can actually pull them out front. I can write this like this. Now, realize what this is the center of mass. Okay, R alpha is a vector. So, for our rigid bodies, we're going to assume our origin is at the center of mass, and we can make this 0. So there we go. So that means we're only left with this term for the rotational. So KE rotational is going to be equal to 1/2 sum M alpha omega cross omega or R alpha squared. Okay. Now, you can write omega crossed R alpha squared as omega squared R alpha squared minus omega dot R alpha. So that's this vector product, and you can look it up in Shams or in probably any higher level textbook where they're using vectors. So we're going to use that, and now I'm going to rewrite KE rotational. Now, the point of what I'm doing, why I'm playing around with the rotational kinetic energy and what your book does, is I want to get it in the form of 1/2 I omega squared. I want it to look something like that. So that's where I'm going. Okay, so I have 1/2 sum all the masses alpha, and then omega squared times r alpha squared. You know, omega is omega 1, so omega squared is omega 1 squared plus omega 2 squared plus omega 3 squared. R alpha is x1 squared plus x2 squared plus x3 squared is r alpha squared. So I'm going to write this like this: sum I equals 1 to 3 omega I squared times sum j to 3 r j alpha squared. Oh no, I'm sorry, x j alpha squared. Then minus, now it's a dot product here, so sum of and this is, it's squared too, so I'm going to have some I w dot r alpha would be sum of I equals 1 to 3 of omega I r I alpha, or x, I'm sorry, x1, x2, x3. And then, because it's squared, the next one, it doesn't have to be I, so I'll make it j to 3 omega j x j alpha. So there's what that looks like now. I'm getting there. I want to pull out the summation signs here, but I got this wi. I'm going to write this like this. I'll just put it that way. 1/2 sum alpha m alpha and sum I sum j. These go 1 to 3. And now I'm going to write, so I have omega I squared, and this would be omega 1 squared plus omega 2 squared plus omega 3 squared. I want to write this for this reason, or for a reason, omega I, omega j here. The problem is they have to be the same. So what I'm going to do is put in a direct delta function here too, ij. That's 0 unless I is equal to j. Okay? And then I'm going to take out, put another summation here. Let's call it over k for the x's. X k alpha squared. So I've rewritten this rather funny, but it's the same thing. Okay, and then this is why I wanted to pull those out, because I have the summation I and j here too. So then I could put minus x. See, because this had omega I and omega j here, I wanted the same thing on this side. And the only way I could do that is put in that direct delta function, so these remain omega 1 squared, omega 2 squared, omega 3 squared. Okay? So I pulled out these summation signs, factored them out, but to get this right now I had to write that like that. And now here I'm just left with, and again I've pulled out this omega and omega j too. That's going to be well, I'll write it back in here too. xi alpha xj alpha omega I omega j. There we go. So now I'm going to rewrite this one more time. I'm going to pull out the omega I, omega j, so I'm going to bring these into summation signs out to the front. Omega I, omega j. And then what am I going to have? What's left is the sum over alpha, m alpha, delta ij sum over k xk alpha squared minus xi alpha xj alpha. There we go. Now this has an omega squared. Oh, we're missing our 1/2. Put it out front. So we have 1/2, we have omega squared, and this would look like this. 1/2, I shouldn't have erased it. It'll look something like that if this is considered to be the I. Okay? So this is going to be our moment of inertia, and it depends on I and J, so we'll write it okay. So now we can write the kinetic energy is equal to 1/2 sum over I equals 1 to 3, J equals 1 to 3, omega I, omega J, moment of inertia Ij. So now it has at least the form that we wanted. So we're going to have I goes from 1 to 3, J goes from 1 to 3. So we're going to write our moment of inertia tensor like this. We'll have I11, I12, I13, I21, I22, I23, 33, or 3-1, I'm sorry, I-3-2, I-3-3. Okay. So let's look, using this formula right up here, what would I-11 be? So we have a sum of our masses, but I is 1 and J is 1. So the delta function is 1. And we're going to have x1 squared, x plus x2 squared plus x3 squared. So we'll have x1 alpha squared plus x2 alpha squared plus x3 alpha squared. Then minus x1 alpha x1 alpha. So that'll cancel that one. And this will be some m over alpha x2 alpha squared plus x3 alpha squared. And let's look at just one more. Let's look at I12. Sum over the masses. Now, I is 1, J is 2, so the delta function goes to 0, and we're just left with this negative. I'll put that out front. Negative x1 alpha, x2 alpha. And I think you can see, for example, if I do I13, it's going to be negative sum alpha m sub alpha x1 alpha x3 alpha, and so on. Now, we're probably not going to be working in here with discrete particles of mass. we're going to be talking about real rigid bodies like a disk rotating or something like that. So there's not countable masses for us. So what do we do? Well, what happens? Let's look at Ri equals sum m alpha delta ij sum of k xk alpha squared minus x I alpha xj alpha. What does this become for a continuous rigid body? Well, you know your summation signs becomes an integral. And since the mass, total mass, well, a certain amount of mass if you want, dm, is equal to density dv, then I will become an integral rho width. I can't take it out of the integration because it might not be a constant. And I have dv, so I'll put the dv over here. And then I have ij, the sum of x squared, x1 squared plus x2 squared plus x3 squared. I'll write that like this for now. And then dv is dx1, dx2, dx3, right? So let's do an example. Let's do something planar. So this is going to be my x-axis, my y-axis. So let's say we have a solid triangle here. So this is a solid triangle, and it's going to rotate about an axis that goes this way and goes off. Let's say the height of this side is a, this is 0, and over here is a. Okay, so I need to write down my formula for the moment of inertia. Now this is an area, so there's no thickness to this, so I'm only going to have an area, and I'm going to use the fact that dm equals sigma d area. So sigma is a mass per area instead of using rho, which is usually reserved for a mass per volume. So then my formula becomes sigma up here, delta ij, sum for k xk squared, minus xi xj, and now I'm going to let x1 equal x, x2 is y. So I'm going to have dx dy out here. Okay, so now I'm set up. I can do find my parts of my moment of inertia. So let's find the I11 term. So I can bring sigma out. I'm assuming it's uniform density. Integration. It's 1, 1, so delta 1, 1 is 1. So I'm going to have an x squared plus y squared from that, because we're going k is 1 to 2 in this case. We only have 2 dimensions we're worried about. Then minus x squared, because that's x1 squared, dx dy. So that cancels that, and we're left with I11 equals sigma y squared dx dy. So I'm going to do my x integration first, and if I look up here as I go along the x, the upper limit changes as I go along. So it's going to start from 0. X is 0, and I'm going to go up to, in general, to some general x up to whatever this is. So the equation of this line should be y is negative slope, a negative 1 x, then I have to add in the intercept. So that would give me x equals negative y plus a. So I'm going to go from x is 0 up to x is negative y plus a. And then when I do that, then I can integrate over all of y from 0 to a. So if you have any questions about that, let me know. Okay, so I do the integration with respect to x first, and I get negative y plus a. I still have my y squared, and now I have only dy from 0 to a. Okay, so this gives me sigma times negative y cubed, so I'm going to get negative a to the 4th over 4 plus a y squared, so that's going to give me a to the 4th over 3. And that's going to be sigma negative a to the 4th over, let's make that a common denominator 12, so I have 3 over 12 plus 4a to the 4th over 12 equals sigma a to the 4th over 12. So there's my I11. Let's do I12. Looking up in my formula, I pulled out the sigma. I is 1, j is 2, so that goes to 0. I'm left with a negative xy dx dy. Same thing, I'm going to integrate over x first from 0 to negative y plus a, and y is going to go from 0 to a then. So I get negative sigma. Doing the x1 first, I'll get negative y plus a squared over 2 times y dy, 0 to a. And that's going to equal negative sigma. I'm going to get y squared minus 2ay plus a squared plus a squared y plus a squared, hold it, times y dy. Oh boy, so it's equal to negative, sorry, I'm way down here, it was negative sigma 0 to a y cubed minus 2a y squared plus a squared y dy. And let's see, what is that going to give me? Equals negative sigma a to the 4th over 4 minus 2a to the 4th over 3 plus a to the 4th over 2. Equals. So that gives me negative sigma a to the 4th over 12 once I get a common denominator. So I have I11 was sigma a to the 4th over 12. And I12 is negative sigma a to the 4th over 12. Now, you can realize the area of this triangle, 1/2 the base times the height. So sigma is the mass of the thing over 1/2 the base times the height. So 2m over a squared. So I could replace that there, and I could have I11 is m a squared over 6. And I12 is going to be negative m a squared over 6. So that's how you do it. So when I get the whole thing, if you want to double check, what I get for my moment of inertia tensor is I'm going to pull out the MA so I don't have to write it all the time. Let's do this again. I equals MA squared times, and I'm going to have 1/6, negative 1/6. We just found this is going to be 0. I'm going to have negative 1/6, 1/6, 0, and then I'm going to have 0, 0, 1/3. So if you want to finish out the rest of these and check, you should. So next time, maybe we'll do one more example. Then we need to show how you use this in practice.